So I could be operating on HF, and I might be able to talk to somebody down in, I don't know, Ontario, but the guy a couple of kilometres down the road saying, sorry, you can't hear me at all. And that's because of skip, and this area called the skip zone. So there's a minimum distance for the skip going up further. So anyone between C and D will be able to hear me. But then the signal's bouncing back up again, and there's a dead zone here between D and E, and then the second bounce comes down here, so anyone between E and F can hear me. Okay, so the signals also can go via multiple paths. That's what we're showing here. We're showing, so we're showing a number of different paths. So here we've got a signal which is bouncing off the F layer, and it's got two hops. We've got a signal coming here that's a single hop off the F layer. I've got a signal here which is sporadic E, so it's bouncing off the E layer. Probably wouldn't have all of those at the same time, but it's an example of the fact that we have a signal arriving at the receiver which has traveled a different route. And going those different routes, it's got a different distance that it's traveled. And whether the signal arrives in phase, that is synchronized with the wave front of another path, or whether it's out of phase, those signals can either add together or they can cancel each other out. So that's a process we call fading. I think we've got another slide later on fading. Yeah, so we can, the signals can go multiple paths and cancel out. What's happening here? Oh, we've got an animation. Oh, there's the signal. Oh, that one's going multiple hops. And there we go.
Does that all have to do with the band, or is that actually focusing a wave?
Right, yeah, it's...
Like your band just radiates like
Yeah.
a circle, but it just ends up...
Yeah, exactly the latter, which is you've got maybe a dipole over here, and so you've got the donut shape of propagation coming out of there. So the radio wave is going vertically, it's going out horizontally, it's going out at an angle. The wave going out this way horizontally gets attenuated because it's just a ground wave and it dies out quickly. The one going vertically doesn't come back because we talk about wide and roller, but it might go straight out into space. The one at the angle does get reflected, so it's just the one that at the right frequency gets reflected. So in the same way when you're doing the skipping of the rocks over the surface of the water, if you don't have the right angle, then it doesn't skip. It plummets straight into the water. So it has to have that right angle and at the right frequency to get that effect. Well, first of all, it wouldn't be. Well, I guess it could be a big Yagi. Yeah. It would have to be a big one. Essentially you do. You probably want, ideally you want an antenna which is going to direct most of the energy out that way. So it's going up to the ionosphere, but mostly out horizontally, because of the curvature of the Earth, if you go out horizontally, eventually the Earth curves around and you hit the ionosphere. So for that reason, verticals are good antennas because most of the energy is going out horizontally, not going out vertically, which So yeah. Okay, so we've got definitions. We've got multi-hop, where it's bouncing multiple times. We've got this idea of the skip zone, which is the area between the transmitter and the first time the signal comes back to the Earth, which is a dead zone. Skip distance, the distance between where it originated and where it lands. And, the effect. So often we talk about this effect of bouncing off the ionosphere as, people will call it a reflection. You reflect off the ionosphere or bounce off the ionosphere. The technical term is diffraction. If you remember the diffraction wave going through the slit, it bends as it goes through a different medium. So the ionosphere is like a more dense medium, and it causes the wave to slow down as it hits it. Well, I'm not quite sure what it does, but the effect is the wave going up is actually bending through the ionosphere and coming back down. So it's not purely a reflection, but it's actually a bending, and we call that diffraction. Reflection, so so we have the wave does actually reflect. So when it comes back down to the ground, it meets, remember where we saw the picture of the mountains and the reflection on the water. It's similar to that. If it hits the sea, it reflects off the sea. The Earth is actually at radio frequency quite a good reflector. So there's a reflection going on here. VHF, UHF, we don't get these effects very often at VHF, UHF frequency. I don't think we ever get them at UHF, but at VHF, under extreme ionization, you can get skip. And we get attenuation, which is the loss of the signal, which is this radius squared loss. Okay, so I talked about this already. This is the skip zone, multiple hops. The idea that we can get an area, a dead area, and then we get the landing of the first bounce, and then we can get the second bit region, and then the second bounce. Again, this depends on frequency. We'll see some charts later where you can see the actual propagation forecasts, and depending on the frequency, you may get, these may merge into a single region, but at some frequencies where they start separating out. Oh, there we go again, with an animation. Alright, so this is just talking about the distances that these signals propagate. If it's a E hop, then it's smaller. The reason for that is the E layer is closer to the Earth, so when it goes up and comes down, it doesn't travel quite as far. The F layer is much higher, so we can get skips of the order of 4,000 kilometers, which is a good exam question. I haven't talked too much about absorption. We're going to talk a little bit more about that, but this chart is in the textbook, figure 6-7, and it really shows the effects of the different frequencies on either the ground wave or the sky wave. So we see at lower frequencies the ground wave is the dominant effect. So at frequencies up to 300 kilohertz, we're getting propagation by ground wave up to about 1,500 kilometers. As we go further in frequency, the ground wave dies out, and once we get up to about 3 megahertz, we really don't get, we can't see the ground wave at all. The skywave is sort of the opposite of that. At lower frequencies, we don't get the skywave because that skywave is getting absorbed by the D layer. Once we get up to frequencies in the HF region, then we start getting the F layer skip, and we get long distance propagation. And then as we continue to increase frequency, we stop getting that effect. So VHF and UHF, the signal goes straight through the D layer and the F layer and out into space, which is why if you want to communicate with somebody in space, you would use a frequency up here in the VHF UHF range. Medium frequency is the interesting one because it varies between day and night. So during the day, you're going to get ground wave, and at night, you're going to get penetration of the D layer because the D layer is collapsed, and then you'll start to get skip at night time. Okay, it's probably time to take a break. It's 10:30, so can we take 10 minutes and have some coffee, some donuts, and